Now, it looks like there's sort of nothing we can do with this, and we don't know what the solution is. However, I claim that if we fit it into this form, we can figure out what the integral is relatively easily by some little magic of cancellation that happens. The idea is the following. If I consider this function to be u, then what's going to appear on the other side in the integrated form is the function u prime, which is, so if you like, u is log x, so u prime is 1 over x. Now, 1 over x is a more manageable function than log x. What we're using is that when we differentiate the function, it's getting nicer. It's getting more tractable for us. In order for this to fit into this pattern, however, I need a function v. So what in the world am I going to put here for v? The answer is, well, dx is almost the right answer. The answer turns out to be x. And the reason is that that makes v prime 1. Okay? That makes v prime 1. So that means that this is u, but it's also uv prime, which was what I had on the left-hand side. All right? So it's both u and uv prime. So this is the setup, and now all I'm going to do is read off what the formula says. What it says is this is equal to u times v. So u is this and v is that, so it's x log x minus, so that again, this is uv, except in the other order, vu. And then I'm integrating, and what do I have to integrate? U prime times v. So look up there, u prime times v with a minus sign here. U prime is 1 over x, and v is x. So it's 1 over x, that's u prime, and here is x, that's v, dx. Now that one is easy to integrate because 1 over x times x is 1, and the integral of 1 dx is x plus c, if you like. All right? So the antiderivative of 1 is x. And so here's our answer. Our answer is that this is x log x minus x plus c. I'm going to do 2 more slightly more complicated examples. And then really, the main thing is to get yourself used to this method. And there's no one way of doing that. Just practice makes perfect. And so we'll just do a few more examples and illustrate them. The second example that I'm going to use is the integral of log x squared dx. And this is just slightly more recalcitrant. Namely, I'm going to let u be log x, the quantity squared. And again, v is equal to x, so that matches up here. That is, v prime is 1, so this is u times v prime. Right? So this thing is u times v prime. And then we'll just see what happens. Now, the gain that we get is that when I differentiate the logarithm squared, I'm going to get something simpler. It's not going to win us the whole battle, but it will get us started. So here we get u prime, and that's 2 log x times 1 over x, applying the chain rule. And so the formula is that this is x log x, the quantity squared, minus the integral of, well, it's u prime times v, right? That's what I have to put over here. So u prime is 2 log x times 1 over x, and v is x. And so now you notice something interesting happening here. So let me just demarcate this a little bit and let you see what it is that I'm doing here. So notice this is the same integral. So here we have x log x squared. We've already solved that part. But now notice that the 1 over x and the x cancel, so we're back to the previous case. We didn't win all the way, but actually we reduced ourselves to this integral, to the integral of log x, which we already know. So here, I can copy that down. That's minus 2 times x log x minus x, and then I have to throw in a constant c, and that's the end of the problem here. That's it. All right? So this piece I got from example 1. Now, this illustrates a principle which is a little bit more complicated than just the one of integration by parts, which is a sort of a general principle, which I'll call my example 3, which is something which is called a reduction formula. A reduction formula is a case where we apply some rule and we figure out one of these integrals in terms of something else, which is a little bit simpler. And eventually we'll get down to the end, but it may take us n steps from the beginning. So the example is the natural log of n to the x to the n power dx. And the claim is that if I do what I did in example 2 to this case, I'll get a simpler one, which will involve the n minus first power. And that way I can get all the way back down to the final answer. So here's what happens. We take u as log x to the nth power. This is the same discussion as before. V is x. And then u prime is n times log x to the n minus 1 times 1 over x. And v prime is 1. And so the setup is similar. We have here x times log x to the nth power minus the integral, and there's n times. It turns out to be log x to the n minus 1. And then there's a 1 over x and an x which cancel. All right? So I'm going to explain this also abstractly a little bit, just to show you what's happening here. If you use the notation fn of x is the integral of log x to the nth power dx, and we're going to forget the constant here, then the relationship that we have here is that fn of x is equal to x log x to the n, that's the first term over here, minus n times the preceding one, this one here. And the idea is that eventually we can get down. If we start with the nth one, we have a formula that includes, so the reduction is to the n minus first, then we can reduce to the n minus second, and so on, until we reduce to the first one, and then in fact we can even go down to the 0th one. All right, so this is the idea of a reduction formula, and let me illustrate it exactly in the context of examples 1 and 2. So the first step would be to evaluate the first one, which is, if you like, log x to the 0 power dx. That's very easy, that's x. And then f1 of x is equal to x log x minus f0 of x. Now that's applying this rule. So let me just put it in a box here. This is the method of induction. Here's the rule. And I'm applying it for n equals 1. I plugged in n equals 1 here. So here I have x log x to the 1 power minus 1 times f sub 0 of x. And that's what I put right here on the right-hand side. And that's going to generate for me the formula that I want, which is x log x minus x. That's the answer to this problem over here. This was example 1. Notice I've dropped the constants because I can add them in at the end. So I'll put in parentheses here plus c. That's what would happen at the end of the problem. The next step, so that was example 1. And now example 2 works more or less the same way. I'm just summarizing what I did on that blackboard right up here. The same thing, but in much more compact notation. If I take f2 of x, that's going to be equal to x log x squared minus twice f1 of x. Again, this is box for n equals 2. And if I plug it in, what I'm getting here is x log x squared minus twice this stuff here, which is right here. X log x minus x, if you like, plus c. So I'll leave the c off. Okay?